So, we looked into OTTV and energy codes in general. So, we look into some of the potential solar energy options before we look into things like ratings. Okay. So, I think we just, I just might have mentioned this sometime earlier. The options are photovoltaic generation is one of the major option. Right, and solar water heating using solar panel. So, out of this is most popular. There are various options, for example, solar ventilation, and similarly there are many others. Now, we will look into this actually. Now, what we know is generally it is currently of the order of around 10 to the power 9 gigajoules per year, that is the data sort of thing, and it is increasing. So, solar energy utilization is gradually increasing, people are getting conscious about it, and let us see what is, look at photovoltaic scenario. So, before looking at that, you see this, we have looked into the heat transfer in buildings sometime or other, or might have mentioned to you. So, there are certain amount of casual heat gain into building and heat gain into the building through fabric, etc., etc. Now, you can capture some of the solar energy that comes onto the building envelope using photovoltaic and any other on-site generation based on this. You can have on-site generation, that is GT, let us say. The load comes from the outside environment and appliances, etc., inside, which is casual heat gain. So, on-site generation, if you can store, that is good, because it will not, on-site generation, say through this or through other kind of sources such as local windmill in the building, very tall building or something of that kind, and this they will not match with the requirement. So, you might need some storages sometime, right, and you might have a metering system as well. So, if you look at variation of solar energy, supposing I have a fixed, I have a fixed insolation collector, IC stands for radiation on a collector. I keep it at a fixed angle of voltage, fixed angle, for example, tilt angle as we call it. So, this tilt angle, supposing if it is horizontal, it is 0. If I keep it at certain angle, beta equals to 32 degree, let us say. So, this is 32 degree, solar radiation falling like this. Then I get, if it is fixed, I get, the radiation received is somewhere here during the day hour of the day. So, around 8 a.m. to 6 p.m. or something. Now, this is fixed at a given angle, while if I keep its angle changed, track the sun, then I get higher solar radiation. So, you can make it automated. So, if you look at that, then supposing I have got, if you see this set of graph for various month, daily average solar radiation, direct radiation per day, kilowatt meter square per day, let us say, then this is fixed vertical. So, vertical do not get, it gets much less depending upon, of course, the month, right. So, say something like summer, vertical gets less radiation because altitude angle of the sun is very high. Altitude angle of the sun is very high, right. So, this is the altitude angle of the sun is, if the sun is here you do not get any radiation. So, supposing altitude angle is close to 90 degree, cos 90 is 0. So, I cos 90, so it will get much less during the summer months. Winter months it gets because sun's altitude is, during winter months sun's altitude angle is lower. So, during winter months sun's altitude angle is lower, therefore, during winter months vertical surfaces get some. So, if you keep the PV on vertical surface, then summer months you are unlikely to get, but winter months you are likely to get some radiation. Now, let us say something this tracking in both axes, this will be the maximum, which means that you keep on changing this angle of this panel, collector panel, you keep on changing both in horizontal as well as in vertical direction. So, when you keep on changing you get maximum in summer months, obviously winter months it will be relatively less because radiation is high in summer months. And tracking axis at tilt angle being latitude. So, keep one angle, but it is in horizontal plane, say this one is horizontal plane, it rotates, but in the vertical tilt angle remaining fixed. That means, this angle remaining fixed, but then it rotates in this plane. This angle remaining fixed, in the vertical plane the angle is fixed, which is tilt angle, but it is rotating in the horizontal plane. So, following the sun, that also you get fairly high. And tracking horizontal, right, tracking horizontal north south axis. So, similarly there are different angle, if you keep it you get different radiation. So, vertical you get least in summer, but winter you get just horizontal, fixed horizontal, let us say is actually this, which you get high in summer, but winter you do not get, but if you have tracking obviously this is understood. So, by doing tracking you can actually trap more energy, you can trap more energy if you do tracking. Okay. So, this is one thing. So, whatever device, whatever system you have, whether it is a water heating system, a flat plate collector, right, which will absorb heat and heat up the water in pipes or in blackened pipes, which we will discuss sometime later on, or a photovoltaic devices which will actually generate electricity. If you do tracking you always get more energy, right. Okay. Now, you see the maximum load in the household is something like this, diurnal daily 0 to 5 am or so, there is no load, but it picks up and maximum load is in the evening hours, because both your lights and your cooling system or heating system, because the space is maximum used, residential spaces are mostly used, also your commercial spaces will be used in the evening time. So, you have a peak somewhere there, house load if you see, or even otherwise any the loads generally you will be seeing somewhere there. But your PV generation is only between 6 to 18, because solar radiation you get from 6 to 18. So, this is extra you are getting here, and these spaces you have to actually borrow from the grid. So, we have this, this is something like this. If I plot energy exported to the grid and local grid load, because during the daytime noon you can actually export some energy, but in the evening you have to get from the grid. So, energy exported to the grid is this, its peak at this point of time, and aggregated local load this is there, but this is here it is. So, basically there is a time during which you will have, you can get from the, you have to I mean you can supply to the grid or store it for later on usage. So, this we actually we can, when we calculate life cycle cost, this becomes important. So, this is what we can see that certain time of the day energy exported to the grid is obviously negative, because you are getting it at that point of time, independently they are plotted. So, minimal energy I actually take from the grid during the daytime, but I have to get it in the evening and so on. So, options therefore, if I look at it for photovoltaic, sometime I have to get and sometimes. So, we define something called E energy from the utility, that is grid. That would be 0.8760 hours, that is 24 into 365, makes it 8760 all hours, maximum between 0 and load minus whatever you are getting from. So, this P stands for power, power you get from the load or P from the solar. Now, maximum of this, that means all negative values will be thrown out, it will be converted into maximum of either 0. So, it can be less than 0. So, 0 P load. So, that is the E from utility, and E from solar to utility is maximum of 0 P solar minus P load, right, and for the whole year, all hours, for all hours actually I calculate out. So, this, all right. So, depending upon variation of solar energy availability, sky condition, etc., this may vary in an hour and can be constant or varying with time. So, you might take hourly values, that itself is good enough, right. So, depending upon sky condition, everything put together. So, this will vary, and therefore, one may integrate over the whole. Now, if I look at the economics part of it, life cycle cost, I will have some initial cost of the system, then rated power, P rated, how much it generates, P rated. There is a operation and maintenance cost, that is also multiplied per unit power, this will be per unit power. So, for generation of unit power, whatever is the cost, that is C initial, and operation and maintenance cost per unit power, that is known to me, multiplied by what is called present work factor, because these are all in different time, and as we sometime might have discussed in engineering economics term, right, this is present work factor. So, this is yearly expenditure, I must bring it to the current level, and this is from initial cost from setting up the facility to get collected from the grid, from the utility, and E from the utility, per, because this will be rated, power rated. So, E is the power from the utility into present work factor. So, this is how it is. This is a cost, sorry, this is a cost from the power, if you are getting from the grid, what is the cost per unit power, and E from the grid I am getting, from the utility I am getting, or might be having my own generator. I mean, that is why the utilities, if I am getting from the grid, is fine. So, this is a per unit cost multiplied by whatever we have calculated earlier, whatever we have seen earlier, whatever we have defined earlier. This is E, this multiplied by cost per unit multiplied by present work factor, and this should be, the signs of these two will be opposite, because this is what I am giving to the utilities. So, this is actually purchase rate, this will be purchase rate, this will be the selling rate, this will be the selling rate, right. So, this is the selling rate, and so this is the purchase rate from utility, and minus this is the wholesale selling rate to utility. So, this is a, so life cycle cost one can work out onto this and compare different systems if they like, right. So, you should minimize LCC, this life cycle cost should be minimized. If it is, if the building envelope is designed properly, then your load will be reduced. So, when you talk like things like net zero building, we actually discussed that there are various factors or parameters we might choose, like orientation, shape, envelope, etc., such that my load is minimal. Load is minimal. So, in that case, this would be relatively less. So, my life cycle cost would be, this should be plus, actually this should be plus, yeah, this plus, this would be less, and this then could be higher. So, therefore, life cycle cost will get lower, right. So, we will discuss one or two, besides this photovoltaic, we will also discuss other system, but let us first look at this. So, what we know is silicon, germanium, etc., these are semiconductors and they are used in photovoltaic system. So, if you look at a periodic table, on the left hand side you have got metals and the right hand side you have got non-metals. In between you have like carbon, silicon, etc. They are somewhere in between. And if you look at metals, they will have the number of electrons in the outer orbit which is far away from the nucleus, they can lose it very easily. So, if you look at the structure of metals, generally it is assumed to be polycrystalline, these are assumed to be polycrystalline, although we are not talking of the material right now, they are assumed to be polycrystalline with all metal nucleus assumed to be spheres, they are packed in a given manner like body centered cubic packing, face centered cubic packing, etc., etc. So, they are packed. So, spherical nuclei they are actually packed in a given manner and packing density is sufficiently large, so that it is stable. What happens is the outer electron they form a kind of a cloud or which can move very easily. So, in metals nuclei which are assumed to be spherical, they are packed and the outer electron are relatively loosely connected to the system. So, as soon as you give some energy, electrical potential, this electron can move, that is why they are good conductors. On the other hand, non-metals they form actually covalent bonds, they form covalent, for example, Cl2, O2. So, two atoms combine together and share the electron of the outer periphery, because where they have less, it is not stable. So, they borrow from the another one and share it to become form a stable molecule. In between ones are such that they do show, they are somewhere in between. So, they do not lose electrons so easily, and this one they do not lose, they can get from somebody or share. Now, in this in between ones, this is what is this one, what is called is energy, the energy level is called valency bond, where in this one the electrons are at what is called conduction band. So, valency band and conduction band. Here between this in non-metals, supposing I give some energy, the electron will not move outside, because the distance between valency bond and the conduction, valency band and conduction band, the energy level is very high. To make it conductor, I have to give very large energy, where if I give a small potential, electron moves. In this one, this is somewhat in between. So, the difference between what called valence band and the conduction band is relatively less than this. Here it is infinite. So, if you give some energy, it can get ionized at very high energy level. So, some gases of course. So, that is it. So, if you look at this, let me erase this out. So, when electron in valence band is raised to a conduction band by sufficient light energy, semiconductor starts conducting. So, semiconductors are in between, metals are conductors, non-metals are insulators. In the periodic table, something in between, they are semiconductors. So, when you supply sufficient light energy, they can start, they can actually start conducting. So, this required energy is called band gap. So, this is the valence band, the balance, there is a band gap between the two energy level, and in conductor the valence band and the conduction band coincides, and in insulator band gap is very large. So, that is what it is, that is what I was just mentioning. So, what is done in this one is valence band, conduction band, and this is the band gap. So, this gap is very large in case of insulators. So, you supply energy, electron will not move. In conduction they almost coincides. So, moment you supply they will move. So, if you supply light in semiconductor, if you supply light, since this gap is relatively less, then the insulator with sufficient supply of energy they can jump onto this one. So, that is the idea, and that is how electricity is generated out of solar cells. So, the energy supplied through photons depends on obviously wavelength, and as you know shorter wavelengths travel, the shorter wave high energy. So, they can travel over, they carry actually high energy. So, sun's energy is short wave which can actually travel through glass, but while we know that long wave it does not. The terrestrial radiation from terrestrial, that is what we talked about. So, shorter wavelengths are associated with more energetic photons. The required energy is called band gap. So, in conductor the balance, as I said, this already I have mentioned. And if I look at the sun's radiation, this is ultraviolet, this zone is visible, this range, and this is infrared. This is, this is average at 5250 black body spectrum. So, sunlight at top of the atmosphere is something like this, and this is at the sea level, because there will be a lot of absorptions in the atmosphere. So, there is some absorptions that take place, all right. So, that is the sun's energy. So, peak is around the visible range, because peak is around the visible range, that is why you see it. And in semiconductor, something like, as I said, in the middle of the periodic table we have silicon or carbon. Let us say silicon you take, its atomic number is 14. It has got of course 14 proton as well. So, atomic weight is 28, but we are not bothered about this. So, if we look at this 14, we know that this is sp, df, etc., you remember. So, these are 2 electrons, then 8, 2 plus 8 plus, outer shell will have 4. So, these are the 4, right. Now, this is a silicon atom would look like, and if I give energy there, then this can jump out, this can jump out, because this 4, if I give energy, the gap between the valence band and the conduction band is relatively less compared to that of insulator, right, or non-metal or the right hand side. So, this can actually jump, but what is, so light causes the electron to jump and leave a hole there, as we call it, So, it is now net effect is a positive charge. So, the pure silicon is amorphous, and even if it jumps, even if it jumps actually, the energy is absorbed and lost. It won't move actually, it will jump and maybe energy is lost and then it comes back again. So, this energy is absorbed and it is as heat converted into heat, and it might come back to it. So, just falls and energy is lost as heat. So, if I have just I supply, it jumps out, but it will generate heat and come back. So, in order to ensure that there is a continuous flow, I must see in some manner the electron that has come out must be able to move to another atom and so on and so forth. So, to ensure continuous conduction, the silicon can be doped with other elements like boron, phosphorus with very small concentration. So, supposing I have a boron or phosphorus, as we shall see, boron has got 3 electrons in the outer shell, because in the same group as aluminum, group 3. This was in the left hand side on the metallic side, and phosphorus is on the right hand side. It has got 5 electrons at the outer periphery. So, let us see. So, this is silicon atom. There are 4 outer electron with each silicon atom we are showing, right. Outer electron, that is what it is. So, that is how silicon looks like. Silicon crystal, supposing silicon atom, now supposing instead I put 1 boron, instead of silicon there is 1 boron. So, I mixed it up, doped it. So, this is the boron atom. Now, it has got 3, instead of 4 silicon I was having 4, it has got 3 electron in the outer shell, 1, 2, 3 instead, So, it has got, this is missing, because boron has got 3, electron in outer shell. So, then there is a gap here, right. The system is electron neutral, because the number of protons here and number of electron, they are all matched, they are same. So, it is electron neutral, there is no problem, right. So, this is what boron is, it has got atomic number 5, right. So, 1, 2 and 3 there, all right. So, I mix this up sometime, still is, and the gap results in hole, that means there is a gap here. So, 1 electron possibly can come here, right. There is a gap, because otherwise it was all 4, 4, 4, here suddenly there is 1, 3. Similarly, if I have phosphorus, which is 15, so 2, 8 plus 5, 2 plus 8 plus 5. So, in outer shell it has got 5 electrons, and I just put phosphorus 1, I have got extra electron there, and again this is also electrically neutral. So, earlier case I had 1 less electron, here I have got 1 more electron, right. So, if I now, if the electron then jumps, the boron one, where there is boron, there is a gap there. So, that gap can be filled up by, if an electron jumps out from silicon, it can go to the boron, and if in case of phosphorus it is the other way around, it has got an excess electron which it can lose easily. So, excess electron can be donated, that this is called donor or N type, and previous one is called P type, previous one is called P type, previous one is called P type. So, the structure is electrically neutral, the gap results in a host which can accept an electron, called acceptors. So, you have P and P junctions you can form, and if you now pass the light, the electron can move from one to the other, because there is a gap available and there is somewhere excess that we like to shed off, and this system can be built together to form what is known as a semiconductor, and they can can be a photovoltaic device that can be formed into a photovoltaic device, right, that can be formed into a photovoltaic device. So, that is what I am saying. So, these junctions are used, right. So, it is something like this, you have p doped semiconductor, you have n doped semiconductor, and you have metal on both the sides. So, when light falls onto this, right, p was the one which would actually accept, and that is what we said, p was what was p, the excess. So, n is the one which can give away. So, p is the one which can accept, actually p is the one which can accept. So, this, when light falls onto it, from the silicon it will accept, right, but then it becomes electrically negative. So, if there is a metal conductor, it will move to the metal, and since the this has actually lost 1 electron, this will supply that electron. So, this process can continue. So, when you have a p and p junction, light falls onto it, the movement of electron can take place, because one of them is an acceptor, other is the donor, and the acceptor can accept the electron that will move out of silicon, and as it becomes electrically negative, the electron will tend to move, and the other one, which is a donor, would also like to reject an electron and the process can continue. So, that is how actually photoelectric devices work. So, that is the diagram. Now, essentially I will have boron, silicon, phosphorus, you can see this something like this structure. Then you have got metal contact somewhere there, metal contact somewhere there, right. And as the light falls onto it, actual construction looks something like this. I will come back to this later on. Actual construction will look something like this, not even this here. This is a better look. So, you have transparent surface. There is a metal here. So, light falls onto this. Now, this is actually N type. This is some depletion layer. There is a P type, and the metal here. So, electron flow takes place from this one, from N type to the P type, N type to the P type. As the radiation falls, as light falls onto this, and there are metal connectors through which the electricity will flow. So, we will be back here again in a moment, but just let us, so that is what it is. So, this is how, but then this will have some, so therefore, it will generate some voltage and you can have some load, then the current will flow through this. So, this is what it looks like, energy levels. Now, there will be losses in the system, there will be losses in the system, so there will be some losses in the system, of course, and that has to be taken care of. So, I would be written as some flux multiplied by A, in this case, okay, we will see that what it is. So, we will look into this. Current in amperes is given by J A, we will define all this. Cell area is A, and we will look into this actually the algebra part of it. So, that is how it looks like, the P type, the N type, and electric field is generated. So, holes diffuse into P type layer, leaving behind a negatively charged region, and electron diffuse into the P type layer, leaving behind a positively charged region, and so on. So, there is a voltage difference created. So, that is the idea, the light falls onto, and so on. So, anyway, how it is important for us, I mean, without going too much into the details of this construction, the electron movement is thus one directional. We will be interested in the efficiency of system, look into efficiency of the system for our usage, how much efficient the system will be. So, some background, little bit of background in this, because they are subject by themselves. So, the electron movement is one directional in this one. So, it is a direct current system, DC. So, whatever light passes causes positive basically. So, it is somewhat, it is all DC actually. So, it is all direct current system, right, and it is one directional. So, people denote it by, okay, this will come later on. So, people denote it by a specific symbol, which we will look into.